Good morning and good afternoon, depending on where you are. Thank you for joining us today. Today, we will be providing an overview of the latest set of enhancements and new functions in LP360 version 2020.1. Before we get started, I would like to go ahead and do an audio check. Please notice the raise your hand button has been circled in red on the slide. If you can hear me, please click this button now. We still have some people joining us, so we'll just give everybody a few seconds. It looks like everybody can hear me. All right, great. My name is Crystal Bailey, and I will be moderating today's session. Joining me today is GeoCue's President and CTO, Lewis Graham, and our VP of Special Projects, Martin Flood, who will be answering questions during this webinar. Before we begin, I would like to go over a few things. Group audio has been disabled for this session. If you would like to ask a question, please use the question box on your GoToWebinar panel. This session will be roughly 60 minutes. If we do not get to your question during this webinar, we will follow up with you by email. This webinar is being recorded and will be distributed to everyone registered. At this time, I will be launching one of 3 poll questions. How frequently do you use LP360 for ArcGIS? And I'll leave this open for a little bit longer as we're still having some people joining us. Alrighty, I'll go ahead and close that poll. And then our last poll before I pass the presentation to Lewis, how frequently do you use LP360? Still getting a few votes in. I'll leave that open for just a second longer. Perfect. I'll go ahead and close that poll. All right, thank you for voting, everyone. Joining me now is GeoCue's President and CTO, Mr. Lewis Graham, and I will hand the presentation over to him now.
All right, good morning. You see my screen okay?
Yep.
Crystal? My
Yep,
voice is okay? All right.
Yep, everything's good.
All right, thank you. Well, thanks everybody for attending. I'll skip over the intro because most of you are customers and already know about our company. We've been here a long time, since 2003. Before that, we were with Intergraph and ZI Imaging. Our headquarters is in Huntsville, Alabama, and we have a satellite office with Mr. Flood in Toronto, Canada. So what we do is 3 major things. We do all sorts of things, but I try to categorize it into 3 major areas. We do enterprise software solutions where we do custom development, primarily focused on some kind of high performance sensor workflow. We do drone mapping. We've been in that since about 2013. And then finally, what we're here primarily to talk about is our airborne and mobile laser scanning solutions, where we sell TerraSolid products and support those products. We do our own LP360 point cloud software, and we have a number of data management tools in that arena as well, such as our GeoCue workflow software and a few web-based data management systems. We also do a lot of workflow consulting and training in those areas. So as far as the airborne and mobile laser scanning business, we think we're the largest supplier of production LiDAR tools in North America. So production is when you go out and fly the data and you process that data until it's ready for analysis. On the analysis side, LP360 Standalone, in my opinion anyway, is the best Windows desktop application for point cloud exploitation, whether that's coming from LiDAR, structure from motion, any kind of point cloud that can be put in LAS or LAZ format. And then of course, LP360 for ArcGIS, it's probably the only remaining third-party application for, or I should say extension for ArcGIS that allows high-performance exploitation of LiDAR data. So ArcGIS has its own built-in tools. I would consider those sort of casual user tools, whereas LP360 for ArcGIS makes that a high-performance environment. So if you look at our LiDAR tools on the, let's say, airborne and mobile side, as well as UAS, then I think of them as 3 tiers. The production tier, so again, this is people who are flying sensors, whether it's drone or manned or mobile. Distribution, how do you get data to constituents, or how do you get it from production to QC, that sort of thing. And finally, exploitation. The exploitation area is what we'll talk about today. So this is where you take the LiDAR data and you're extracting information from it. Boy, I've got an old name still hanging on this slide, Topolis. That was a brief naming we were using for the UAS side of LP360. But we have a large installed customer base. It's a global customer base, and it ranges everywhere from academic users at universities to large production companies that have many seats of LP360. For information, we have a knowledge base. You can visit it, support at knowledge at geoque.com. And go ahead and join our LinkedIn group. We're getting, Crystal's been a lot more active on LinkedIn. We're posting more useful information there. So if you would, join our GeoCue group. LP360 comes in far too many versions, but the basic stacks are the standalone 64-bit for Windows. This is the on the left, and this is the application that gets most of our attention these days in terms of development. We have LP360 for ArcGIS, and you'll see that we continue to add a lot of capability to that product. And then we have a version of LP360 that we use for our new UAV sensor line called TrueView, and we've named this product Evo. It is LP360 advanced with some special tools for processing either data from our own TrueView sensors or a few guest sensors. For example, we have a version that you can process data from a Phantom 4 Pro RTK, and we consider that a TrueView guest sensor. It's localizable, so we have it localized to 5 languages now. So into the new features. So we've got a long shopping list, and we'll provide you copies of these slides. So I'm not going to go through and read all of these new features, but this first list are features that we've added to both the standalone version that's just simply called LP360, as well as LP360 for ArcGIS. So this went into all versions. And of course, anything that any feature that's in LP360 will also be in TrueView Evo if we have any TrueView Evo customers out there listening to this. So we had a lot of focus. Live View is the tool that we have in LP360 that allows a lot of different visualization modes. And I think every release we wind up adding more things to this. The fact that we've built our own LiDAR sensors for drones has really made us focus a lot on how can we improve live view such that you can do more analytic sorts of things, like how can I visualize multiple beams from a multi-beam laser scanner and see the comparative performance between them, things of that nature. Point cloud tasks are our engine for doing, they're primarily for batch processing, although most of them allow interactive use as well. We'll see some demos of a couple of those today that I'll use in both modes. And so we continue to add capability to this. One really interesting classifier that we've added that I'm actually not demoing today is a proximity classifier, and that says that if I have points in a particular point cloud, I can see how close they are to points in another point cloud and reclassify them based on some classification, and some nearness tests, some proximity tests. Yeah, and then on standalone only, a few, I have not included on this list features that are unique to Evo. That's a separate webinar. So these are tools that you could use if you were doing drone processing using one of our TrueView sensors, but you could just as well use them for airborne mobile laser scanning. You could use them for point cloud from Imagery and so forth. So, you know, a miscellaneous collection of things that have improved the feature edit capabilities of LP360. So we have a lot more import formats that we recognize now, and we've added a few additional export formats. So this is for vector processing within LP360. A few other tools of that nature, a couple of custom tools that were obviously done for specific customers, such as our Tapa Seawall Collection tool, which was done for the city of Miami Beach. In today's webinar, I want to focus on a few tools that I think really stand out. So one of them that we'll just see peripherally is that the new point clouds are becoming quite dense. So it's not unusual to have point clouds that are several hundred points per square meter. You know, and we used to think that, say, power line data at 50 points per square meter was super dense. And now with drone operations, density has really gone up quite a bit. So we've done a lot of work in our point cloud tasks and other tools, I should add, to handle these very dense data sets without having to do unusual things like thin the data before you do a ground classification. So we want to be able to work with this raw data. It's pretty challenging. We have a new data smoothing filter that we've added, and I'll give you a demo of this. If you're doing any kind of drone mapping, you need LP360 just for this. This tool alone will pay for your investment in LP360, no question about it. So improved visualization, some new feature QC tools. So let's move right into it. The first one is something that I call class modulated visualization. Let's just jump over here to LP360. And so what we have, and you're going to see a lot of examples of drone collected LiDAR data. It happens to be what we work with quite a bit now. And so what you're seeing on this particular screen is some TrueView 410 data. And I've turned off the Google backdrop. So this is LiDAR imagery from our TrueView 410 sensor. That's a Quanergy laser scanner with dual RGB cameras. And then in part of the TrueView Evo processing, we colorize those points as RGB. So this is LAS points, but it's colorized in a really nice, you know, directly from the camera. So this is really stunning data. But something that's better than just the visual appeal of it, yeah, sure, it looks really good, but it really helps with classification identification. So if I'm going to classify something, you know, which is the better view? You know, I can look at it in an elevation view, which is a traditional view. And yeah, I can make out, I think, what is a tree, and this has the possibility of being a building. I think I need to look at it in 3D. I can look at the data with intensity, and that may or may not be helpful. The Quanergy sensor doesn't have the best gray level or IR response, but I can make out features. But really, you know, the place where it really is impactful and I can tell what's going on is in this color view. But I have a problem if I'm in this color view. So I'm in the color view and I want to classify, say, to ground. How am I going to know what I've classified? You know, so I could come along and say, oh, let's manually classify a little bit of stuff to ground. So I'll just draw a little, I don't know if this is ground or not, I'll draw a little area here. And now I've classified it to ground, but I've got to toggle over to a different view to see that. Now I have to view by class. And now I can see that little patch that I colorized, or that I just classified to ground. And you can see that this is a pretty awkward environment to go back and forth between colorization. So what we've done is we've allowed you to modulate or add or replace, I should say, replace in any view using a bit of an override. So I'll bring up live view, and you see a new column called blend. And if I check this column, when I press a blend toolbar button, which is this tool here on my toolbar, it's going to override all pixels, if you will, or all points in the display with the classification color, if that class happens to exist. So here I've got ground selected. Let me drag this out of the way, and I'll turn on my modulate by color. And what I'm going to do is combine this with another little demo, which is ground classification. So I'm just going to interactively classify using the automatic ground classifier, a little bit of area here. So I'll just drag a rectangle. So right now I'm running a point cloud task for ground classification. And those of you who have used LP360 with this very dense drone LiDAR data in the past, you would recognize that what I just drug would typically take several minutes to classify. And so you can see we've really done quite an improvement on this performance of this point cloud task in this very dense data. So I'm really happy with that. And now notice this new blending button. So if I turn it off, I get my normal display. If I turn it on, there's everything that I classified as ground. So you can see that this is a much more usable way to do classification than the typical I have to be in one channel of view. And it works in other views. I don't have to just be in RGB. If I'm with standard LiDAR data that is not colorized, I can still use this capability. So you can see that I'm visualizing by elevation, but I've blended in my ground class. And I think over here, I might have classified some other items. So I could bring up live view, and I might have classified some, let's say there might be a little bit of building, and maybe I've got some water in here. And then you notice that it has indeed modulated these other colors as well. So you can have more than one class that you're modulating into the color scheme. And of course, I can do this as well in other views. So let me draw a profile view. And here in the profile view, I'm showing data by classification, but let's switch over to something like, let's do color down here. And so here you see the standard colorized display of the data. And I click the modulate, and you see the ground class showing through here. So this is really quite a nice feature. All right. Check my notes and see if I've shown everything. Yes. So debiasing point cloud data, this is important for people that are doing production work or are doing UAS work. So if you're going to measure the vertical accuracy of LiDAR data, the ASPRS, the American Society for Photogrammetry and Remote Sensing, uses root mean squared error between the LiDAR data and a set of checkpoints to assess the accuracy of the data. And we know that's RMSE vertical Z. So if we look at the contents of this, really what we're doing is we're just taking the difference between a control point and the point cloud. We call that the residual. This is what I call RZ. And we just sum up all those residuals squared. We just square it because we don't want negative points that are below the point cloud to cancel out ones above. So if we square it, it's essentially the same as taking absolute value, square root thereof. And anyway, so we have this formula for root mean squared error. But if you take root mean squared error apart, you discover that the root mean squared error is equal to the bias, or the mean value of the residuals. That's this first term, r with a bar over it squared, plus the variance for the standard deviation squared. So what this tells us is that if there's any bias in the point cloud, we could reduce the error, the vertical error, by removing that bias. So how do we remove the bias? So this process is called the Z bump. Everybody in production does it. So they go out and figure out the mean value and say, okay, I'm going to shift the whole LiDAR point cloud to improve accuracy. And this is a perfectly valid operation because the bias is systematic and you can remove systematic errors. The question becomes, when am I allowed to do that? And there isn't a rule that I could find about that, but I think a good rule of thumb that we here at GeoCue have developed is, let's look at the standard deviation of the mean. So we'll look at the deviation of the mean itself. And if that is a small value relative to the bias itself, then I am valid in moving the mean. So it's the uncertainty of the mean, right? The standard deviation of the mean. If it's a really small number, then the mean is, my error is in the residuals is pretty much systematic and I can shift it. But if I have a really large standard deviation of the mean, it means that I've got a big spread in the deviation of the residuals relative to their own mean. So anyway, this gives us a really nice mathematical justification where we just argue that if the bias, that is the absolute value of the mean of the residuals, if that minus the standard deviation of the mean is greater than 0, then it's legitimate to debias. And that sounds a lot more complicated than it is. Let's go back to LP360 and let me load up a different project. Do I want to save you? I guess so. Well, it's asking me all kinds of exit questions because I made a bunch of modifications while I was in the software. So for example, I changed my filter for live view by adding some of those modulated classes. And so I've saved that as a new filter in live view so I don't have to make it up the next time. All right. So here we are in a new project. Zoom to this layer. Turn off my Bing aerial. All right. Let me exit this and come back in real quick. So in this example, we want to talk about the debiasing of LiDAR data. We'll open up our project. And we will look at some data. This data is from a TrueView 615. So this is a Regal class instrument. We get much higher fidelity with this. But let's have a look at, this is a test range that we fly, and we've got some checkpoints over this test range. And let's go have a look at the accuracy of these data. So I'm going to do an inverse distance weighted sample. I think this is more valid for this very dense LiDAR data that we use from drone LiDAR systems. And the first thing I'd note to you is that we've made some changes to this dialog, and all of you that are measuring accuracy, even in QC of airborne or mobile data, have used this function before. And it lets you bring in a set of checkpoints, 3D up to 3D checkpoints, because you can do planimetric X, Y individually and also vertically. Right now we're going to focus on vertical. We've added a new quick set capability, or else I think we're applying it such that it actually works. I can say I just want to look at, say, full check, and this will filter out operations in the data that are not full check. So for example, the base station's been automatically filtered out. So this is just toggling. It's just convenient toggling off a field that's in your checkpoint file or in your control point file if you're using them for control points. And to run the error calculation, I just press the Calculate DZ button. My checkpoints are far in excess of the extent of the LiDAR data, so it's just warning me that, hey, some of these checkpoints don't have any LiDAR data. And it tells me at the bottom that, hey, it measured 11 vertical points. And over in this section of the dialog, I can see what the results of that are. So I have a mean vertical error of 2.7 centimeters, as you can see down here, units or meters. I've got a standard deviation of the mean of 7 millimeters. So the standard deviation of the mean is much smaller than the mean. That means that it's a pretty tight mean. It's pretty much, I'm pretty much guaranteed it's a bias and not just random noise that's causing me to have this mean error. If these were reversed, say, and I had maybe 1 centimeter of mean error, but a standard deviation of the mean of, say, 2 centimeters, then all bets are off, and I shouldn't be doing any kind of debiasing operation. So my total root mean squared error is 3.5 centimeters, so 3.5 RMSE. That's a really nice project. Let me do a capture of this so that I've got it available. And what we're going to do now is we're going to run a point cloud task to debias these data. So our mean error is 2.7 centimeters. And so I want to do, this point cloud task is called an affine transform. And it lets you shift LiDAR point cloud, or any kind of LAS point cloud, I should say, by either rotate, scale, and translate, or you can apply an entire transformation matrix to the data. So you'd apply a transformation matrix, for example, if you knew the transformation, say, from a projected coordinate system to a LSR plant system, would be an example where you use that. Well, let's get to it and add we want to shift this by 0.02 centimeters. So I put that in as a Z translate. I apply that. Let me shift this data over a little so we can see it. And we're going to run the point cloud task on this entire data set. And you can see that it's generating a new set of LAS files for all of the data that I had in this original TrueView 615 project. And that's giving me the progress up here. This goes pretty quickly. And we'll have this new shifted data. And we're done. And of course, this is colorized data as well. I'll switch to this new layer that we just created, and I'll say, well, I prefer the the color rendition. So let me change the visualization to color. And yeah, that's a really nice thing about LP360 is that you can manage multiple layers of LAS data within a single project. So that's really nice when you're doing temporal changes. So you're doing borrow pit and you need more than one temporal date in the system. So it makes it quite nice for that. All right, so with this new debias, let's go look at this accuracy once again. We're still set up the same, except now we're using this new shifted LAS layer. Let's calculate the vertical. And now you see that we have a mean error of 0. Well, we better because we just debiased the data, right? That's what we shifted it by. And we've got a root mean squared error now of 2.2 centimeters. So you see that we reduced that root mean squared error from 3.5 centimeters to 2.2 centimeters. So that's one of the first steps that you would do when you're doing a LiDAR project, whether it's a countywide LiDAR project, which is a little more complicated because you have to do it blockwise. You can't do a single operation. But for drone projects, where you typically have the entire project loaded into the system at one time, then this is a really good standard practice operation, I would say, to get the kind of accuracy that, or to remove that bias kind of accuracy. Now, the only thing we don't tell you how to do, and this is a tool I really want to add to LP360, is we don't tell you anything about your distribution of checkpoints. Do you have a good distribution of checkpoints or do you have a weak distribution? A weak distribution would be where you had them all in one single spot, whereas a strong distribution, you've got them well distributed throughout through the project. You take a little look at some piece of this data in the 3D view. And you can see that this is colorized LiDAR data from our Regal system using our dual mapping cameras as well as the Regal Minivux 2. That's a 200 kilohertz Regal scanner. And you can see that the data quality is just remarkable. I mean, this data is just gorgeous. And this is processed directly off the sensor. The only thing we've done is the debiasing operation that you just observed. All right. And we'll close out of that one. So that's really nice. So we added additional tools to the control point dialog. We've added this new affine point cloud task. Now, to be honest, we had that before, but we had it combined with a geodetic transforming tool, and that made it a little bit difficult to use. So we've split that into two separate point cloud tasks now. It makes it easier to use, especially for debiasing of LiDAR data. So we built, I think probably 2 years ago, we added some really nice feature QC tools to LP360 standalone. These are not in the ArcGIS version, for doing things like checking break lines, and particularly for checking constrained geometry such as downhill constraints. How can I how can I do QC on these kinds of products, and how can I find out where the errors are and that sort of thing. And then we had a request earlier this year from USGS, who uses these tools a lot for QCing of LiDAR data and break line data for LiDARs and water body boundaries and so forth. They said the tools are great, we like to use them, but we don't have an easy way to communicate errors to our contractors. And so we collaborated with USGS to add a new tool for collaboration. And let's have a look at that now. Start LP360 up. And load a new project. Move my PowerPoint. And for this one, I'll load up, let's see, a mine site. And what I did is I previously just playing around. So this is a pretty deep mine. If we look at a profile across here, scooch this up a little bit, and then you can see the profile of this, the cross section of this profile that I've drawn. What it is, I draped a few features in here that really don't mean anything. I draped one down the road and then a couple just moving down this bank. And let's just have a look at how that goes. So I'm going to bring into the feature edit toolbar this, what I call downstream layer. And I'll just digitize a feature along here. So I'll just do a 2-point feature, but I'll tell the system to do a drape. And you can see when I click the first point, the profile is showing where that point landed. I'll double click to end that feature. And then LP360 will go do a drape on it. And here, let me fatten up my profile a bit. And so here in the profile, you can see that it nicely drapes that feature right on the surface. And so that's just one of the many, many digitizing tools that we have in LP360. But what we're interested in is what is the quality of these features. And so I'll bring up this feature layer in our tool Feature Analyst. And we have the notion in Feature Analyst of analysis, hence its name. And so we can do general tests like, self-intersecting, planar tests. So, I might use this for stockpile toes, for example, and say, do I have any very sharp angles in my toe geometry? So I can look for min and max angles. Vertical is usually the most interesting for LiDAR data. And so we've got, is it uphill? Is it downhill? Hey, is the feature actually flat? And then I can look at what's the minimum Z and, all sorts of different tests that I can do on the vertical part of features. I can look at size, minimum line lengths, maximum, so forth. Then I can look at M values. And if you're not familiar with the shapefile format, and M value it's just a fourth coordinate on every vertex that you can put into the feature file. And it allows you, well, you can use it for anything you want. So for example, on a downstream constraint, where we readjust the vector so that it's always going downstream, we use the M value to say, how much did we have to move a vertex to obey this downstream constraint? So for this particular test, on vertical, let's just look at downhill. And I will tell the system that I want to apply this test. And so it says 2 of these features have passed the downstream constraint. They should, because I used our downstream constraint tool to digitize them, but 3 of these have failed. And so if I go in and look at the failed feature, I can go look at its vertices, and it will actually tell me where it failed. So I just scroll down here, and there's a red X on the downhill test. So it failed at this vertex. I can click on the this point, and I'll be driven. Let me zoom in on the profile a bit so we can actually see the vertices. And I get driven exactly to that error. So this is very cool. This is not new. We've had this in LP360 for a while. So this is telling me, hey, the next vertex after the one you've selected is higher than this vertex, and therefore you have violated the downstream constraint. I click to the next one, same sort of thing, but the next one, of course, is okay because his next vertex is downhill. So you get the idea. So we had this great analysis tool, and customers like USGS and NOAA and so forth are using this tool to analyze their vectors, and it makes life a lot faster, a lot happier, because it's quite quick to find all of the errors. But if I'm not going to fix them myself, how do I convey those to someone else? So like I say, we collaborated to add a new tool. And this new tool allows us to do an export of two things. One of them is export the features themselves, just a shapefile. And then the other thing is export the failed or past conditions. So what I want to say is I want to export all my features that have failed the test. So I click, I could do pass and failed or just passed only, but typically it's failed that I want. And then there's a choice to say, where do you want to write these two shape files? One is going to be the failed feature. The other one is going to be a set of vertices that mark all of the failed locations. And so I've done that, and I've added these to the map. Let me turn off the original downstream. So here's the features that failed. 3 features failed, so I just duplicated them because I might want to send those to my contractor. But more importantly, what failed? And I indicate that simply by generating vertices. So I generate a vertex at every failure. Now, normally in something like a downstream, I would only have a couple vertices. I wouldn't have this many, but you get the idea. So every one of these is pointing to some sort of failure. If I go inspect the attribute data of this particular point, you can see that it's got the failed test. The test was downhill and it failed. So all I have to do now is, if I go send the original vectors, let me go to the table of content, along with these failure vertices, then this will tell the contractor exactly where your vertex failed and why your vertex failed. Now let's look at one other thing while we're in here. I'm going to go back to my original vector set and bring it back into Feature Analyst. And go to the Feature tab, and I'm going to go into my test, and I'm going to keep my downhill here, but I'm going to go over and look at M values, and I'm going to say, you can see I was playing with this before, if my M value exceeds 25, a quarter of a foot, I want to know about it. So what this says is that on downstream constraint geometries, even if they pass the downstream test, I want to know how much the vertex had to be moved. In other words, how much was the geometry fudged to achieve that downstream constraint? So that gives even more visibility into it. So here we can see that we've got 2 features that passed the downstream constraint, but they failed this movement of M value. And again, I can go, so here's just one location where it really had to move a vertex a long way. I can go zoom into this. So I'm still passing my downstream constraint, but you can see this is a pretty low point to the right of this point. So it was probably originally digitized at, say, at this level, and then it was pushed down to meet the constraint. And we can even look in here and see that it was pushed down by 0.4 of a foot. So anyway, lots of very powerful QC capabilities within LP360. And now we have a way to deliver those QC results to a contractor or user and so forth. All right. So the next thing we want to look at is data smoothing. Like I said, this is a tool that if you do any kind of UAS operations, particularly if you use Velodyne sensors or sensors of that class that are pretty noisy, this is a tool that you'll definitely want to investigate. And so we'll have a quick demo of how this works. And we'll start up LP360 and load that particular product. And I apologize, for some reason the GoToWebinar environment seems to eat a lot of my processor resources, and it tends to slow everything down. So we'll look at a road project. And this was flown with a TrueView 410 Quanergy sensor not too long after we first released the system. I think this was August of last year. It's a really nice data set. So you see this TrueView colorized 410 superimposed over a Google backdrop. And the first thing I want to show you is a new little handy tool in the profile view. And let me go ahead and redraw that profile while I'm at it. So we'll cut a profile across here. And let's make that guy 0.5 meters good. And we added a new tool. If you hold down Control and hit the graticule button on the profile, we added a new tool that'll let you quickly make a uniform graticule. So if I want to make, say, a 10 centimeter graticule, I can just put in 10, hit this button, it populates the whole dialog, say OK. And now it's redone my grid. And if I zoom in on this profile, you see that I've got an envelope of about 20 centimeters of spread in this data on this hard surface road. And what I want to do is I want to go in here and I want to do a bit of measurement. So what I'm going to do is I'm going to digitize some what I call synthetic control points on this road using a point cloud task. So what I'm going to do is I'll click a point. And the system is going in and it's finding the average height at that point in the LAS data. So it's doing a summary around where I'm clicking and conflating a Z value onto the shape feature, this point shape feature that I've generated in LP360 using this so-called conflation point cloud task. And what I want to do with this is I want to use it to measure the average height of this road surface point cloud. So what we'll do is we'll simply go into the control point dialog and we'll use these points as a test. Now, I wasn't very careful in where I place these and so forth. So, if I were doing a real detailed analysis, I would use a little more care in how I put this together. This is in meters, so let's go out, say 0.5 meter. And we'll measure the mean error. And you can see that in this particular data set, we have a mean error using this set of points of, it's literally in the noise, 4 millimeters. So we can say essentially there's no bias here. But I don't like this noise envelope. So I want to go in here and of course, the mean value in that test better be 0 because I collected these points directly from that LiDAR data. They're going to be used for a test later on. They're meaningless at the moment. I was just using the LiDAR data to generate them. So what we're going to do is go to a smoothing point cloud task. And it allows us to filter in data to say, well, I don't want to smooth everything. I just want to smooth the ground class, for example. In my case, I'm going to smooth everything. And I'll apply this again project-wise. No, I won't. Let's just apply it to this area that I'm looking at here. So let me drag an envelope just over this area. So this is a least squared geometric smoothing algorithm that essentially tries to fit surfaces to the original data and then uses those results to shift the point cloud data in such a way to reduce the noise envelope. And so you can see that it's telling me that it's processing, across this block that I drew. It's running a lot slower than I would like. Again, really eating up my machine resources. But through this process, it's data, again, it's trying to adjust a geometry surface that it fits in a local way, but it is done such that it connects to X local fit surface so that we don't have discontinuities in the data. And the result of the operation is a much smoother point cloud surface. And again, I apologize that I'm having some sort of major on my machine at the moment. And I'll tell you what we're going to do. I'm just going to terminate this because we'll be here another few minutes doing it. And I actually have a surface that I've already and we'll have a look at the result of that. All right, bring LP360 back up and load our project. And then we'll examine the before and after of the smooth data. So here we've got the original LAS data being viewed in this profile view. And then if we toggle to the smooth data, you can see the dramatic effect this has on the noise envelope of the data. And the remarkable thing is that even though it has reduced the noise envelope of the data, it does not change the mean, the test that I was in the process of showing you a bit ago. And it also does not destroy features. So you can see that even though I've smoothed the entire data set, and I am looking at the smooth, I still have my transmission line. So I've not sort of eliminated those in the noise removal process. You can even see in the corn that I've not destroyed the rows of corn, etc. So this is quite a remarkable smoothing tool. And the really nice thing about it is that when you apply it, with a lot of smoothing tools, if you want to smooth a road, you have to go draw a polygon around the road and say only apply the smoothing to that surface. With this, you can apply it pretty much project-wise. If we do a test on what happens to the mean of the data before and after the test, the mean does not change. So you won't affect the mean part of root mean squared error, but you actually can improve the noise composition piece of it. And then let's look at one final quick example. We're doing some work for a little bit of experimental work with the Department of Agriculture using 5-band cameras. In this case, it's the MicaSense Altum. We're not doing any processing of Altum data or 5-band data within LP360, but we definitely want the ability to display the data so that we can bring it in and say, oh, how did it turn out? Can we have an analysis of it? And so we've added a few new tools to raster layers. So if I pop up to the property, so we've always supported N band where N is greater than 3, but now we've added some capability to make it easier to use. So for example, if I want to look at band 4, which happens to be the red edge for this data, then I can lock all my bands together, set one of them to band 4, and then I'm going to get the red edge in a nice monotonic view, and of course, monotonic view. And of course, you can see the red edge chlorophyll effects from that. If I'm in normal display mode, I can display in color. And then finally, normally when you're doing RGB imagery, when you're applying a stretch to the imagery, which you have to do with these greater than 8-band images, then it takes the statistics from all 3 bands and combines those to apply a stretch. And you typically get a color pattern that is not the desired pattern. In multispectral, you typically want to do independent stretches. And so we've added the capability to do independent stretches. And you can see that that makes quite a bit of difference in the data. All right. So I apologize for that performance issue that required me to kill the smoothing operation. But it really brings me to the summary where, I think that LP360 for ARC is the serious tool for that kind of work. We've not started on a port to ArcGIS Pro yet because Esri hasn't given us what I would call a deep integration API. And I think standalone is, you just get an immediate investment you get an immediate return on your investment if you're doing QC. If you're doing any kind of feature collection from point cloud data, we have a plethora of tools. And if you're doing UAS work, this is a must-have tool. There's so many tools in here now for UAS work that, you'll earn the investment in the product back in very short order. And with that, I'll turn it back over to Crystal. Thank you very much for your attention. I appreciate it.
Thank you, Lewis. All righty. All right, so at this time, I will be launching our last poll question. And it's simply, would you like us to contact you concerning acquiring LP360 or updating your license? I do handle our maintenance renewals, so if you'd like to email me directly, my email is cbailey@geoque.com. We can get you back on your maintenance. I'm going to go ahead and leave that open. Again, thank you for attending our webinar today. We hope you continue to stay healthy and safe. This webinar has been recorded and we will be distributing it to everyone who is registered. Thank you again, and we hope to hear from you soon.